radical and rational exponents. So we've seen how to work with square roots, but now we're also going to look at cube roots, fourth roots, etc. So here are a couple of examples of radicals. And in order to work effectively with radicals, you need to know some of the perfect squares, cubes, quartics, which would give us fourth roots, and quintics, which will give us fifth roots. So if you want to pause to jot this down, and then I have some additional perfect squares. You have seen this chart, so you may already have this in your notes. And then there's a few more perfect squares down here. Okay, so we're going to take a look at, first of all, evaluating some perfect roots. So the fourth root of 81 would look like this in radical form. Any even root, such as a square root, what we've been working with a lot, has two answers, both a positive and a negative. If you think about multiplying a number by itself an even number of times, you will always get a positive answer. So you can only take even roots of positive numbers. And the fourth root of 81 is 3, because 3 times 3 is 9, times 3 is 27, times 3 is 81. All right, our second example, we're looking at a cube root. And you can take a cube root of a negative number, because a negative times a negative times a negative is still negative. So negative 2 times negative 2 times negative 2 gives us negative 8. So odd roots only have one answer, and you can take odd roots of negative numbers. So now we're going to look at simplifying radicals. We've seen how to simplify square roots. So this is some review, but now we're throwing some variables in there. So I'm going to split this up one piece at a time. The square root of 48 is 16 times 3, 16 being our perfect square. When you're looking at variables, I'm going to show you this the long way, and then I'll talk about the shortcut. So a cubed, I can split that up as a squared times a. B to the fifth is b squared times b squared times b. Remember, when we multiply variables, we add the exponent. So the 2 plus 2 plus 1 gives us the 5. And then c to the fourth is c squared times c squared. So take the square root of all the perfect squares. The square root of 16 is 4. The square root of a squared is a. For the b squareds, we would have b times b, which gives us b squared. And same for the c squareds. We'll have c times c, or c squared. And then everything that's not a perfect square stays under the radical. So we have 3ab left under our radical. The shortcut, when you're looking at these, is that any variable with an even power is a perfect square. So rewriting this as b to the fourth, if you notice, the square root of b to the fourth was b squared. So what happened was, because this is a square root or a second root, we took our exponent here and divided it by 2, which was the root that we were taking. So if we want to extend this further, we can think about, if we're taking the square root of a to the sixth, 6 divided by 2 is 3, so that's our new power. The square root of a to the 20th, when we take 20 and divide by 2, would be a to the 10th, and so on. Taking a look at b, we're now looking at cube roots. So what I'm going to do on this one is combine them under one radical. Because we're taking the same root, we can combine them. If those were two different roots, we would not be able to combine them under one radical. So I'm going to go ahead and multiply. 12 times 6 is 72. And a to the fourth times a to the fifth is a to the ninth. Let me rewrite that so it looks a little neater. Oh, that's not much better, sorry. So then we look at perfect cube factors for each of our terms. So this is where you have to think about that chart. And 8 is a perfect cube. And 8 times 9 gives us 72. Now with cubes, what we're looking for is multiples of 3. So when you're taking a square root, you look for multiples of 2. When you're taking a cube root, you look for multiples of 3, and I'm talking about exponents here. So this 9, because 9 is a multiple of 3, a to the 9th is a perfect cube. So when I simplify this, I'm going to take the cube root of 8, which is 2, the cube root of a to the 9th, I'm going to take my exponent, 9, divide it by 3, which is my root. So I get a cubed, and then I have the cube root of 9 left over. So let's take a look at working with some ratios under radicals. All right, so our first one, we have square roots, so we're used to seeing this. So I'm going to split these up as perfect squares. 25 times 5 gives me 125. And then x to the 6th, 6 is an even number, so I'm going to take that exponent and divide it by 2. And then I'm going to split up my radical in the denominator as well. So as I simplify my square root of 25, I'm also going to rationalize my denominator. So I have 5 times x cubed times the square root of 5 over the square root of 6. So I'm going to multiply by square root of 6 over square root of 6 to rationalize that denominator. And because they're both square roots, I can put them under the same radical, 5 times 6. And then the square roots cancel, giving me 6 in the denominator. Taking a look at the next one, again, I've got 2 perfect cubes, so I can put those under one radical. But I have to rationalize the denominator anyway, so I'm going to hold off on that until I rationalize the denominator, and then I'll simplify everything together. So looking here, 12 is a multiple of 3. So I'm going to take the cube root of x to the 12th, which is x to the 4th, divide that exponent by 3. And then y to the 4th, remember, can be split up as y cubed times y. So the cube root of y cubed is y, and then we had a y left under the radical. For 32, again, we have to find perfect cube factors. This one again is 8. And what I'm actually going to do, because of the way that you have to rationalize a denominator when it's not a square root, I'm going to leave this in its exponential form, which is 2 squared. So the cube root of 8 is 2, and I have the cube root of 2 squared left over. Now when you rationalize a denominator with a root that is not 2, you're not multiplying it by exactly the same thing. What you want to multiply by is something that will get that radical to cancel, meaning I want to multiply 2 squared by something that will give me a perfect cube. And because I left that in radical form, I know that 2 squared times 2 is 2 cubed, which is a perfect cube. So I am going to be multiplying numerator and denominator by the cube root of 2. I'm going to erase my work here so I can keep working down the page. So when I simplify this, my numerator, I have x to the 4th y, and then under the radical, I've got the cube root of 2y. In the denominator, again, looking at this work right here, when I multiply these together, if I put those under one radical, I'm going to have the cube root of 2 cubed. So the cube root and the cube will cancel, leaving me with 2, times this 2 will give me 4 in the denominator. And the last one, I have 2 different roots, so I cannot combine them under one radical. So I'm going to look at the numerator, simplify my perfect cube, and this is 5 cubed times 5. So the cube root of 5 cubed is 5, and there's a 5 left over under the radical. And this is the same thing, x cubed times x. So the cube root of x cubed is x, and under my radical, I will have 5x left over. In the denominator, the 5th root, and you can think of this as a -1, and take the 5th root of each piece. So the 5th root of -1 is -1, and the 5th root of x to the 5th is x. So I'm gonna simplify. My 5 divided by -1 is -5, and my x's will cancel, leaving me with the cube root of 5x. Alright, I know especially this part B here, rationalizing a denominator that is not a square root is some challenging information. So tomorrow that will for sure be one of our review skill warm-ups, is taking a look at that so you can ask your questions then.